Welcome back to the deep dive. Today we are getting our hands dirty with one of the most classic yet difficult problems in the industry: credit card fraud detection.
And we aren't just talking high-level concepts today.
No, we have a full stack here: a Python machine learning pipeline, execution logs, some very telling visualization charts, and a specific data set from David Ija credit card fraud detection.
It's a great stack because it really highlights the difference between, textbook data science and the messy reality of production. We're going to walk through a random forest implementation that's designed to tackle the imbalance problem.
And that is the core tension of this entire deep dive. I was reviewing the results in the source material, and there's this glaring contradiction. We have a model that achieves 99.95% accuracy. I mean, in any other field, you'd pack up, go home, and ask for a raise. But here, as we'll see, that number is basically a lie.
It's a dangerous lie, actually. If you rely on that accuracy metric alone in a fraud detection context, you're essentially opening the vault door and letting the thieves walk right in.
So let's build this from the ground up. Steps 0 through 3 in the source script cover the data landscape. We're loading a data set via Hugging Face, converting it to a Pandas data frame. We've got about 284,000 transactions. But the columns are, well, they're weird. We have time, amount, and class, which are straightforward, but then we have V1, V2, all the way up to V28.
Right. And if you look at the head of the data frame in the logs, these aren't integers. They're floating point numbers with deep decimals. V1 is like -1.359. V2 is -0.072.
That has to be PCA, right? Principal component analysis.
You nailed it. This is standard operating procedure for financial data. Banks can't release a data set that says John Doe bought a latte at 9 a.m. So they run the original features.
Which could be anything: location, merchant ID, device type.
Exactly. They run it through a dimensionality reduction technique like PCA.
So for the listeners who haven't run a PCA recently, essentially we're projecting the data onto new axes, right? We're taking a high dimensional space and sort of squashing it down into these 28 principal components that explain the most variance.
Precisely. These V features are just linear combinations of the original sensitive data. They preserve the mathematical relationships, the patterns you need to distinguish normal from fraud, but they strip away all the human context. So V14 might be a combination of distance from home and transaction amount, but we'll never know for sure.
The only thing they didn't transform is time and amount, and of course the target variable, class. 0 for normal, 1 for fraud. Now, before we get to the scary imbalance part, I have to point out something in step 2 that it gave me this bizarre sense of satisfaction. The data quality check.
A wall of zeros.
Yes. The execution log lists missing values per column for all 31 columns. And it is just 0, 0, 0, 0.
It's the unicorn of data sets. I mean, in the real world, you spend 80% of your time fixing broken data imputing missing ages, standardizing state abbreviations, dealing with nulls. Here, the data set is pristine.
No imputation needed.
None.
Which means the team could focus entirely on the algorithmic strategy, and they needed to, because the class distribution it's a nightmare.
Nightmare is the technical term, I believe.
I'm looking at the Dataset.pn chart. It's a count plot. The bar for class 0, normal, is this massive tower reaching up past 280,000. The bar for class 1, fraud, is, well, if you squint, you might see a pixel.
The numbers from the script tell the story. 284,315 normal transactions against just 492 fraud cases. That's a ratio of 99.83% to 0.17%.
This is what we call a severe skew. And this dictates everything that happens next in the pipeline, doesn't it? Because if I'm a machine learning model and my goal is just to minimize error, the smartest thing I can do is just guess normal for everything.
Precisely. That's the zero or baseline model. If I built a model right now that just printed false, regardless of the input, I would be right 99.83% of the time. I'd have high accuracy, but I'd have zero utility because I'd catch zero fraud. The challenge here isn't just prediction. It's forcing the model to care about that tiny minority class.
So let's see how they prep for that battle. Segment 2, preparation. They drop the class column for the features, obviously, but they also drop time.
Which is an interesting choice. The source notes call it non-informative. In some fraud models, the velocity of transactions, how fast they happen, is key. But here, the raw timestamp, just the seconds elapsed since the start, it probably doesn't carry enough signal compared to those PCA features. It's just noise.
Better to prune it than let the model overfit on it. Now, step 5 is the train test split. And here we see the first critical tactical move against the imbalance: stratify.
This is absolutely non-negotiable.
Explain why. Because usually a random split is fine, right?
Think about it. We only have 492 fraud cases in the entire universe of this data set. If we just randomly grab 20% of the data for our test set, there's a statistical probability, a small one, but a real one, that we grab almost none of the fraud cases. Or, conversely, we might accidentally grab all of them for the test set and leave none for training.
So the model would either have nothing to learn from or nothing to be tested against.
Exactly. Stratify locks the ratio. It makes sure that if 0.17% of the total data is fraud, then exactly 0.17% of the training set is fraud and 0.17% of the test set is fraud. It guarantees representation.
Okay, so looking at the logs, the split puts 394 fraud cases in the training bucket and 98 in the testing bucket. Those 98 are our needles.
Those 98 are the only thing that matter.
All right, let's build a brain. Step 6. They initialize a random forest classifier. Now, for those listening who know their algorithms, a random forest is an ensemble method. It's not just one decision tree, it's a whole parliament of them.
Right. It relies on bagging or bootstrap aggregating. Essentially, you create multiple subsets of the data allowing for duplicates and train a separate decision tree on each subset. Then, for a new prediction, all the trees vote. If 20 trees say fraud and 10 say normal, the forest predicts fraud. It smoothens out the errors of individual trees.
But I noticed something in the hyperparameters that made me pause. Nestimators, 30.
You caught that too.
30 trees. That feels incredibly low for a data set with 280,000 rows. Usually I see 100, 200, maybe even 500 trees in a production random forest. Why so few?
It is an aggressive choice. It could be for computational speed. Fewer trees mean faster training, faster inference, or it could be a crude way to prevent overfitting. With such a small minority class, sometimes a massive forest ends up memorizing the noise in the fraud cases rather than the signal. But honestly, in a real production environment, I'd expect this number to be higher. 30 trees makes the model a bit more volatile.
However, they did include the single most important parameter for this problem, class weight balanced.
This is the heavy lifting.
So how does the math on this actually work? We said earlier the model wants to be lazy and just ignore the fraud. How does balanced stop it?
It changes the loss function, essentially the penalty score the model gives itself when it makes a mistake. Without weights, a mistake on a fraud case costs the same as a mistake on a normal case. But with class weight balanced, the algorithm calculates weights that are inversely proportional to class frequencies.
So because fraud is roughly 500 times rarer than normal,
the model effectively gets penalized 500 times more for missing a fraud case than for mislabeling a normal one. It artificially inflates the size of the minority class. It forces the trees to split based on patterns that separate the fraud, even if those splits define a tiny sliver of the data.
it makes the needle look as big as the haystack to the algorithm.
That's a great way to put it.
So we've trained the model, we've weighted it. Now comes the moment of truth. Step 7 and 8, evaluation. And this is where we have to become detectives because the headline numbers are misleading.
The accuracy fallacy again.
The log shows an accuracy score of big .9995. That is 99.95%.
It looks perfect. It looks like we solved crime.
But we know better. Let's look at the confusion matrix in step 8. This grid tells the real story. We have a test set of roughly 57,000 transactions. Let's look at the normal rows first, the class 0.
Okay, so we have 56,864 transactions that were actually normal. The model predicted normal for 56,860 of them. These are our true negatives.
And it predicted fraud for only 4 of them. Those are the false positives.
That is an exceptionally low false positive rate. Think about the user experience. A false positive is when you're at a romantic dinner, you hand over your card, and the waiter comes back and says, it was declined. It's humiliating. In this model, out of 57,000 people, that only happened to 4 of them. That is a very low friction model.
But now, the bottom row, the fraud row, we had 98 actual fraud cases in this test set.
The model caught 74 of them. Those are the true positives.
And it missed 24.
False negatives.
And there is the rub. 24 fraudsters slipped through the net. They swiped the card, stole the money, and the model said, have a nice day.
This brings us to the precision and recall scores in the logs. Precision for fraud is 0.95. That means when the model accuses you, it's a 95% sure it's right. That tracks with the low false positives, but the recall is 0.76.
Meaning we only recalled or found 76% of the total fraud. We left 24% of it on the table.
And this is where the source material gets really interesting, technically. Steps 9 and 10 give us 2 charts, the ROC curve and the precision recall curve. I feel like a lot of people treat these as interchangeable, but in this specific scenario, they tell completely different stories.
They do, and understanding the difference is what separates a junior data scientist from a senior one.
Let's start with the ROC curve. The chart shows a blue line that just shoots up almost vertically to the top left. The AUC, the area under the curve, is 0.9536.
which historically is considered an A grade. But here's the trap. The ROC curve is plotted using the false positive rate on the x-axis.
And the formula for false positive rate is false positives divided by
False positives plus true negatives. That's the denominator.
and our true negatives are massive. It's 56,860.
Exactly. Because the normal class is so huge, that denominator is gigantic. Even if we had 100 false positives, 100 divided by 56,000 is still a tiny number. The sheer volume of normal data suppresses the false positive rate, which makes the ROC curve look fantastic. It lets the model hide its mediocre performance on the minority class behind its excellent performance on the majority.
It's grading on a curve where the easy questions are worth 99% of the grade.
Correct. Which is why we need the second chart. Step 10, the precision recall, or PR curve.
The PR curve.png, this one looks different, it's jagged, and the AUC is lower, 0.8662.
This is the source of truth. The precision recall curve doesn't care about true negatives. It never even looks at the 56,000 normal transactions. It calculates precision true positives divided by predicted positives and recall true positives divided by actual positives.
So it completely ignores the haystack and focuses only on the needles and the things we thought were needles.
Right. And when you strip away the credit for getting the easy ones right, the score drops from 0.95 to 0.86. That 0.86 is a much more honest assessment of how well this random forest is actually catching thieves. It reflects that we are missing roughly 1 in 4 fraud cases.
So if I'm the chief risk officer at this bank and you bring me the ROC curve, I'm popping champagne. But if you bring me the PR curve, I'm asking questions.
You're asking, how do we get that recall up?
So to recap the journey today, we took a pristine but massively imbalanced data set. We used PCA features to respect privacy, we used stratified splitting to ensure we didn't lose our rare fraud cases, and we deployed a weighted random forest, admittedly with a curiously low tree count, to fight that imbalance.
And we learned that while the ROC curve made us feel like superheroes with a 0.95 score, the precision recall curve gave us the sober reality of a 0.86 performance.
Showing us that we are catching most, but definitely not all, of the bad guys.
And that the missed cases are likely a calculated cost of doing business.
And that's the thought I want to leave you with.